Ladies and gentlemen, it is a great pleasure for me to attend this seminar and to present a part of our research on the synthesis of silver-doped mesoporous oxides for hydrogen production via water dissociation. In my presentation, I will first pose the problem followed by the proposed solutions. I will then move on to the synthesis of pure and silver-doped mesoporous titania and CO3O4 and their characterizations. I will then move on to the production of hydrogen by photocatalytic dissociation of water on the prepared materials. I will end my presentation with a general conclusion and perspectives. Annual global energy demand is estimated at 15,000 megaton oil equivalent. This energy demand is growing with the increase of world population, which is expected to exceed 9 billion people by 2050, and the annual energy demand could increase fivefold. It is estimated that there will be just over 30 years of use left for oil and natural gas, and about 100 years for coal and nuclear resources. In addition to this problem, there is the environmental problem. The use of fossil fuels, coal, oil, and gas causes numerous public health problems. Emissions of gases such as carbon oxides, which are responsible for acid rain and the deterioration of the ozone layer, and climate change. As a solution, we can mention hydraulic energy, solar energy, wind energy, and biomass. One of the most studied solutions in recent years is hydrogen, associated with fuel cells, a substitute technology for the combustion engine. Using hydrogen. It is the only non-carbon fuel and therefore no CO2 emissions. It is the most abundant chemical element on Earth and it is non-toxic. Also, it has a high energy density per unit of mass. Hydrogen is therefore an energy carrier of the future. It is one of the most promising choices, provided that the processes for its production are environmentally friendly. Photocatalytic water splitting for the production of hydrogen under solar energy irradiation is considered a promising strategy to solve energy and environmental problems. Under light excitation, electrons in the valence band of titania move to the conduction band, leaving a positive charge or a hole, denoted H+, in the valence band. Oxidation of water by photogenerated holes gives protons, which are reduced by photogenerated electrons to give hydrogen. The photoactivity of most semiconductors is restricted to UV irradiation, and the recombination of electron-hole pairs is rapid. To overcome these limitations, different approaches can be considered, including the deposition of metal nanoparticles. Photogenerated electrons can migrate from titania conduction band to the middle, allowing to considerably decrease the direct recombination of electron-hole pairs. The metal particles can also catalyze protons to hydrogen reduction reactions by transferring the electrons to the reaction medium. The objectives of this work are the development of photocatalysts with the potential in the production of hydrogen by dissociation of water under visible light irradiation. Titania was prepared by soft template method as indicated. SBA15 was also prepared by soft templates. Cobalt oxide was prepared by hard template as shown in this scheme. Silver doping was done using a simple method called impregnation reduction by tribasic citrate. We studied the structural and textural evolution of mesoporous oxide using X-ray diffraction, UV visible diffuse reflection, and nitrogen adsorption. Diffractograms of pure and silver-doped titania show lines attributed to the anatase phase of titania and that this structure is maintained after silver doping. We note that for silver contents of 0.5%, the diffraction lines are shifted towards the 2 theta, toward the lower 2 theta, which can be explained by the incorporation of the larger Ag plus cations into the Ti for post-tetrahedral positions. Note also that the silver-doped materials are better crystallized than pure titania, suggesting that the silver species catalyze the recrystallization of the oxide during doping. The diffractograms of CO3O4 and 0.5 Ag on CO3O4 show the characteristic lines of CO3O4 and that the structure is retained after silver doping. As for silver-doped titania, the characteristic silver lines are absent on these diffractograms, and the silver doping improves the crystallinity of the cobalt oxide. In this table, we note that the gap energies of mesoporous titania and cobalt oxide are lower than those reported in the literature for the corresponding non-porous oxides. It is important to note that the silver doping of these oxides resulted in the decrease of their gap energies. This decrease is explained by the fact that the silver nanoparticles introduced localized energy levels in the gap band of the pure oxides. The figure shows the adsorption-desorption isotherms and pore size distribution of titania and cobalt. The table shows the textural properties of mesoporous titania and CO3O4. In conclusion, silver-doped mesoporous oxides are better crystallized than pure mesoporous oxides. The characteristic silver peaks are invisible on the X-ray diffraction patterns, whatever the nature of the oxide, thus indicating that the metal particles are well dispersed on the surface oxide or present in too low quantities. The values of the gap energies of mesoporous titania and CO3O4 are lower than those reported by other authors, which could be attributed to the mesostructure of these oxides. Silver doping decreases the gap energies of the prepared mesoporous. The catalysts synthesized in this work were used in the production of hydrogen by photocatalytic dissociation of water under visible light irradiation. The test was carried out in a pyrite-reacted reactor under these operating conditions. Under irradiation, two types of phenomena occur: photolysis and photocatalysis. Under irradiation, the sacrificial agent is excited and then oxidized by hydroxide anions to give SO4 2-, water and electrons. SO3 2- is oxidized to give S2O6 2- and electrons. The electrons produced before will reduce the water to give hydrogen and hydroxide anions. The irradiation of the photocatalyst causes the departure of electrons from the valence band to the conduction band, leaving holes in the valence band. The electrons will migrate to the middle and the holes oxidize SO3 2-, and the electrons reduce the water to give hydroxide anions and hydrogen. These figures show the amount of hydrogen produced as a function of time. Note that for pure and doped CO3O4, the amount of hydrogen produced beyond 20 minutes is negative, which could be explained by the fact that the production of hydrogen by photolysis of Na2SO3 becomes preponderant compared to that obtained by photocatalysis. It is important to note that whatever the oxide used, the silver doping exalts the photoactivity of the oxides. It is interesting to note that pure CO3O4 is active under light radiation. Young et al. Reported that the production of hydrogen by photolysis of an aqueous Na2SO3 solution increases with the irradiation time, which explains the decrease of the amount of hydrogen produced by photocatalysis when the irradiation time increases. The exaltation of photoactivity after silver doping of oxides is attributed to the decrease of their gap. Silver nanoparticles act as electron traps, promoting interfacial charge transfer and reducing charge recombination. The optimum amount of hydrogen, 1.93 millimole per gram, is produced on 0.5% Ag on mesoporous titania after about 20 minutes of irradiation. It has been reported that on Ag supported on mesoporous titania nanofibers, the optimum amount of hydrogen, 2.5 millimole per gram, is produced after about 5 hours under visible light irradiation. In general conclusion, silver doping decreases the gap energies of the prepared mesoporous oxides. The photocatalytic activity of mesoporous oxides in hydrogen production is exalted after silver doping. Na2SO3 is not a suitable sacrificial agent. The production of hydrogen by photolysis of Na2SO3 in aqueous solution is significant. 0.5 Ag on titania is a potential catalyst for the production of hydrogen by photocatalytic dissociation of water provided use a suitable sacrificial agent. Mesoporous CO3O4 is also a potential candidate as it is active under visible light irradiation without any dose. Study the perspectives study the influence of different sacrificial agents which would allow us to determine the appropriate sacrificial agent for each of the oxides. Study the influence of the other dopants and co-dopants, and using wastewater instead of fresh water, which should make it possible to clean it up and produce energy, is one of the great challenges of the research. Thank you for your attention.